Power method, numerical practical by C programming. Welcome, dear students. Problem 22. Write a C program to compute the dominant eigenpair of the following matrix correct up to 4 decimal places by the power method. This is the matrix 4 by 4 matrix 6.44p minus 2.34, 1.04, 1.67 minus 2.34, 4.68 plus p and so on, where p equal to 2.5 plus r by 20. R is the last digit of your C roll number. Here dominant eigenpair means the numerically largest eigenvalue and the corresponding eigenvector. Now this is a beautiful PDF from net. We get is the definition of dominant eigenvalue and dominant eigenvector. Let lambda 1, lambda 2 and lambda n be eigenvalues of an n by n matrix A. Lambda 1 is called the dominant eigenvalues of A if modulus of lambda 1 greater than modulus of lambda I equal to 2, 3 up to n. The eigenvectors corresponding to lambda 1 are called dominant eigenvector of A, matrix A. And this is the power method. This power method, this x1 equal to A into x0. And this x0 is the initial approximation of some column matrix A x0 column matrix. This matrix x1 equal to A into x0, x2 equal to A into x1, and this x1 equal to A into x0, so A square into x0 and so on, xk equal to A to the power k x0 for large powers of k, and by properly scaling this sequence we will see that we obtain a good approximation of the dominant eigenvector of A, and this procedure is illustrated by the example this. So this is a 2 by 2 matrix and initially chosen non-zero initial column vectors is this column matrix is the x0 1 1, and this x1 equal to ax0, x2 equal to ax1, x3 equal to ax2 and so on, and this, and ultimately we get this. Determining an eigenvalue from an eigenvector. If x is an eigenvector of a matrix A, then its corresponding eigenvalue is given by lambda equal to ax dot x whole divided by x dot x. This quotient is called Rayleigh quotient. This is the Rayleigh quotient, and this example, the previous example from 2, A is the 2 by 2 matrix, and this x6 equal to 568 190. This x6 equal to 568 and 190. So this we get this with x equal to this 2.991 as our approximation of the dominant eigenvector of A. We use the Rayleigh quotient to obtain an approximation of the dominant eigenvalue of A. First we compute the product Ax and this Ax. So A is the given matrix and this X is the this 2.99 1.00, and this equal to X equal to this. So Ax dot X equal to this Ax this dot X 2.99 and 1. This equal to minus 20, and X dot X equal to 9.94, and we compute the Rayleigh quotient, this lambda equal to minus 2.01, and this is the good approximation because this matrix is this 2 minus 12 1 minus 5, 2 minus 12 1 minus 5, and the corresponding eigenvectors eigenvalues are lambda 1 equal to minus 1 and lambda 2 equal to 2. By these characteristics polynomial we get this. So numerically largest eigenvalue minus 2. So by Rayleigh quotient we easily find from the largest eigenvector we get this. And this power method is scaling and so on. This is the convergence of power method. If A is an n by n diagonalizable matrix with a dominant eigenvalue, then there exists a non-zero vector x0 such that the sequence of the vectors ax0, a square x0, a cube x0, a to the power kx0 approaches a multiple of the dominant eigenvectors of A. And the following theorem tells us the sufficient condition for convergence of the power method. This theorem is the sufficient condition. This if a diagonalizable matrix with dominant eigenvalue, then we find this, but not sufficient, not necessary condition. So this is the proof of this theorem, and this and beautiful proof of this theorem, and this is this and the rate of convergence and so on. I will provide this PDF in the description box. Now here this is the matrix. First we define the size 200. So if we change this dimension, this 200, say 300, so we size x size z size z size nz size, and the variables float variables, this pt and this integer variable are these. Here the order of the matrix n is equal to 4, obviously 4 by 4 matrix, and r is the last digit of your roll number, and p equal to 2.5 plus r by 20. It is given that p equal to 2.5 by r by 20. You must put 20.0. The given matrix A is equal to A11, A12, A13, 14, A21, A22, A23, A24, and this A41, A44. And the value of the initial non-zero column matrix X, this X11, X20, X30, X40. If you put x1 equal to 0, and this is 0 matrix, so the method fails. So must put this non-zero column matrix, this x. So at least one of these x must be not equal to 0. Now we print the matrix A. This is the print the matrix A and the corresponding column matrix X, initial column matrix X. Print this. Next we go to the calculation of this power method. This k equal to 0, k is the number of iteration, and this do loop k equal to k plus 1, and print the number of iteration first k equal to 0 plus 1, that is 1. First k equal to 1. For I loop I equal to 1, I less than equal to n I plus plus, zi equal to 0, for j equal to 1, j less than equal to n, j plus plus, zi equal to zi plus aij plus xj. Here initial zi equal to 0. Actually this initial this A matrix A with matrix multiplication with the column matrix X. So this Z gives the product of the A into X. This given matrix, this A 4 by 4 matrix, and this X0, this indicates within brackets indicates the initial approximation. So this 1 0 0 chosen by you, and this first iteration, this A into X, the given matrix A, and this x0, so we get product of the matrix is this, is called this matrix is the numerically largest value, this 8.94, and this take common from this, and so divide by all elements of these column vectors by 8.94, and we get this into this, and say this equal to lambda 1, and this equal to x1, x for the iteration 1, x column vector for the iteration 1, lambda for the iteration 1. This lambda is the actually at this step, step 1 is the largest eigen value, and this is the largest eigen vectors for this step. So here z actually this z actually here this z actually here this is the z, this is the z, a into x, this is the we call this zi, call this zi. Now we store this zi in zi, say, we store the corresponding elements z column vectors to nz to rearranging the elements of z. So to rearrange the elements by bubble sort technique, this the highest to find the numerically largest highest element, the minimum and maximum element. So we get this by this ascending order. We get this z minimum equal to nz1 and z max equal to nzn. So this is the actually renaming of this. nz1 is the maximum and nz is the minimum. nz4 is the minimum value. This z minimum equal to nz1 and z max equal to nz4. This. Now choose the numerically largest element. If this z minimum absolute of z minimum is greater than of absolute of z maximum, if z minimum is negative sign, but this -10 and z max is 4, so z min is absolute, z min is maximum, absolute z min is -10, minus or -10 equal to 10, which is greater than 4. So z max, then we say z max equal to z min. So here we choose the numerically largest element, that is here the numerically largest element is from these elements 8.94 minus these and this. Now 8.94 is the numerically largest element here. Now divide each element x by the z max. So zi equal to zi by z max. So this is the divide this. So divide each elements of this by 8.94. So this equal to 1 and this equal to minus 2.0.261745 and 1 by 0.4 and 1.04 divided by 8.94 is equal to 0.116331 and this 1.67 divided by 8.94 is equal to 0.186801. So divide all these elements, these z max, and they check the tolerance level. Now we check this iteration going on, and now this e1 equal to 0, initial e variable, this e1 equal to absolute for f fz zi, absolute value of zi minus absolute value of xi. So absolute value of xi is the previous step xi and zi is the present stage zi. So actually we calculate this previous step is equal to x0, this 1, and compare this 1, this 1, and present stage this 0 and corresponding elements this and this and this. We check this. So absolute value of this ei, now say e max equal to e1, say. Now for I equal to 2, I less than equal to ni plus plus, if E2 is greater than Emax, then Emax equal to E2. And so check this for each element ei, this is the difference of this absolute zi minus absolute of xi. And this check this corresponding maximum this, and if this Emax is the tolerance level, say 0.00001, and then we again enter in the do loop, and this is the do loop. Again we enter the do loop, here the do loop, this is the do loop, and when this is satisfied, this is true, Emax is greater than this, the difference is greater than the tolerance level, we again compute the iteration, again compute the iteration, that is the do loop. Now for I equal to 1, I less than equal to ni plus plus, xi equal to zi. So for the next step, this xi, new value of xi, actually this is the zi. So from this, this is the this is the zi. So we call this a xi, new for the next step. For the next step, this is the xi, and for the next step, k equal to 2, a this is the given matrix A, and x1 is the previous step, this x1 called it x1, multiply this and we get this A into x1 is this, and this numerically largest element is this, and divide each element by this numerically largest element, and we get this equal to lambda 2, that is the lambda for the step 2, and this is the x2 is the column vector x for the iteration 2. And in this way, and next iteration k3, a into x2, that is a is the given matrix and x2 is the this column vectors. So multiply a into x2, we get this, and find the numerically largest elements, this 10.44, and this divide each elements of this column matrix by 10.445, and so on. We get this 10.45 into this. So this equal to lambda into corresponding x, and this is the lambda x1, lambda x2, lambda x3, lambda x4, and this lambda, this x1, x2, x3, x4, and so on. So ultimately we get this, and this is the numerically largest eigenvalue of this corresponding eigenvector is this, and we find this. So first save, compile and run. We This is the uh, after successful compilation run, enter the value of r, this equal to 0, say put this. So we get this the iteration, this the key is the number of iteration, the first column, second column lambda into x1, third column lambda into x2, lambda into x3, lambda into x4, lambda x1, x2, x3, x4. For this k equal to 1, when k equal to 1, lambda into x1, lambda into x2, lambda into x4, lambda into x4. Actually this lambda x1, lambda x2, lambda x3, lambda x4, actually the given matrix A into x, we get this lambda x1, lambda x2, lambda x3, lambda x4. So from this given matrix A, this given matrix A, and this matrix X, initial X matrix, we get this. This is the 8.94 minus 2.34, 1.04, 1.67, and we get this 8.94 minus 2.34, this lambda x2, 1.04 or 04, this is the lambda x3, 1.67, this is the lambda x4. The numerically largest value, this is called lambda, this is equal to 8.94, and divide all these elements by this 8.94, we get this x1, this is equal to 1.0. This 1.0, and x2 equal to minus 0.26174, this x3 equal to 0.116331, and x4 equal to 0.186801. So this is the first this lambda x1, lambda x2, lambda x3, lambda x4 gives the product of this matrix A and this x, and this lambda is the numerically largest value, and this x1, this lambda into x1, this into this equal to this. So lambda into x2 equal to this, lambda into x3 equal to this, and lambda into x4 equal to this. And for the step 2, this is the x1, x2, x3, x4. We multiply this matrix A with this x1, x2, x3, x4, and we get a x, this is equal to, we get 9 point this 3 minus 3.7, 1.95, 2.64, and numerically largest value is this 9.98, and this divide all these elements by 9.85, and we get this x1, x2, x3, x4. This is called this is called this is called a capital X2, this for second iteration x2, and ultimately we get 98 iteration here, large number of iteration, 98 iteration. This is the, and this lambda 11.86, actually the largest eigenvalue, and this 0.26 804 and 0.397610, 1.0, 0.403623, the numerically largest eigenvalue this, and corresponding eigenvectors is this. Now if you check this the verification for this whether this ax equal to lambda x, this calculation is okay, is correct or not. We check this, uh, this part must be deleted from the programming for verification of this. Now we check this r equal to 0, put here. So you get this verification ax equals to this column matrix 3.18, 4.71, 11.86, 4.78, and lambda into x, this lambda is equal to 11.86, and also get this. So ax equal to lambda into x. So obviously this ax this equal to uh, ax equal to lambda satisfied this. And from the this part, delete this part. And so the programming for largest eigenvalue of a matrix, square matrix, non-zero square matrix is, find this. Thank you and for watching this video.